Water availability is a great factor for growth, health, and productivity of any farm crops, needing careful attention to maximize crop quality and quantity. Local farmers still use the traditional method of soil moisture hand test to determine such, which requires expertise in doing. Crop Water Stress Index or CWSI, a modern method, offers a direct, more accurate, non-invasive, and easy way of measuring the water availability in a plant. The idea of CWSI has been researched for many years, which is gradually gaining a popularity and application in some large automated farms.
The methodology of the CWSI is divided on two major aspects: the theory, which focuses on a statistical model and in yielding the mathematical equation, and system design, which executes the goal of determining CWSI from the theory. In theory, the value of CWSI is computed from the three major variables which determines the rate of evapotranspiration: the air temperature, the canopy temperature, and the relative humidity. In order to do that, we need to perform series of data gathering of these three variables and use the Penman-Monteith equation to solve for the evapotranspiration rates, the VPD or the vapor pressure deficit, and the vapor pressure gradient. Then, we will plot these values as x and y and use regression analysis to yield for the characteristic equation to be used in determining the index through interpolation. Once the mathematical model is complete, electronics design of the control system and power management as well as the programming is to be developed. The entire system of CWSI meter is consisting of sensors to measure the three variables: the microcontroller for performing algorithm, power components for power management, and transducers for user interface. Now, let's go to the data analysis. As mentioned in the methods, we use regression analysis as a statistical tool to relate the effects of our independent variables TA, TC, and RH. By tabulating the vapor pressure deficit and the difference of canopy and air temperature and perform regression, we will yield for the following characteristic equation and the coefficient of determination for the non-water stress baseline. As we see for early vegetation, we have 0.43 of coefficient of determination with the following equation: 0.77 for early flower, and 0.27 for mid-flower. For the result of volumetric water content with CWSI equipped irrigation, the soil water status, CWSI, and water irrigation has been tabulated. Then, comparing the manual water treatment with the CWSI equipped one, we see also that 19.48% of water in millimeter was conserved.
If properly designed and developed, CWSI meter can be built to be readily available for use in irrigation and farming management in the country. A handheld system consisting of sensors and other devices for evaluating the crop water stress index in the different stages of maize crops on a non-water baseline was developed. The major contribution of this study is the development of a low-cost electronic, non-destructive meter for maize crops that can readily measure the CWSI in a quality almost similar to the ones developed in the genuine methods of CWSI approach. Remote sensing through CWSI seems to be a key method for agriculture in today and for the future for farming, water conservation in irrigation scheduling and timing, and in producing quality crops. In summary, this will improve the efficiency of the agricultural sector in the country.
Recommendations for the Crop Water Stress Index Meter. Additional functions such as irrigation scheduling algorithm can be added to the system, in which it automatically irrigates the crops whenever it detects drought. The extension of the scope of measurement of CWSI for other crops can also be taken into account, and that the level of measurement of the remote sensing for this can be added to the controller's program. Moreover, memory function can be included to store the data gathered, which will be used for farming management and irrigation scheduling. And lastly, CWSI accuracy can be greatly improved by using Six Sigma and design of experiment such as full factorial analysis when analyzing and gathering data.